All right. So I seem to be recording now. So welcome again. Let me share a screen of the slides with you. Okay. So okay, we are this week we are covering the logic part of the class. What we'll do today probably corresponds to sections 1 to 4 in chapter 1, but I'm not sure we'll cover this today or not. We'll see how fast I go. Okay, we go rather. All right, let's jump to it. So what is logic? So it's the first discrete mathematics structure that we are going to talk about, a kind of algebra, if you will, where every variable has only 2 values. So the extreme case of being discrete, there is only 2 choices for anything that you talk about, okay? Like extremely non-continuous, okay? Although that's a loose notion. So it's an algebra where everything has either true or false value. And it is incredibly relevant for anything in computer science, right? So first of all, everything we're going to say maps directly onto digital logic, so Boolean circuits. So all the logical operations really go one-to-one with circuits. And perhaps you also know that circuits are equivalent to software. So everything that you can state as an algorithm can be mapped as a circuit and vice versa. So it's a hardware-software equivalence that is very much the basic of computer science. Okay. It's the same type of logical reasoning will be immediately useful for anything in artificial intelligence. So anything there is really stated as a bunch of constraints, which are, first of all, logical constraints. And anything you want to state about an algorithm, are actually about a circuit, or about a network, or about any other, computer science object, a database, what have you, is like, for example, that is correct, that it has certain behavior, certain input-output behavior for a certain class of inputs, that it has some additional properties like liveness, security, privacy, or what have you. All of this you will use logic to express, okay? It will be some quantified formula for all variables of this type. As long as some conditions are met, then okay. So we start from this because you need this language to state everything in a precise way and to be able to read constraints, requirements, conditions. Okay, that somebody else wrote. Okay, and interpret them. So a proposition is a statement that is either true or false. So here is a statement, 2 + 3 = 5. It's a statement which happens to be true. Therefore, it's a proposition. But a false statement, that 3 + 4 is 6, it's a false statement, but there's a proposition. It's a proposition which has a false value. 4 is a prime number. That's also false, but it's a proposition. You can assign a truth-false value to it. It is raining today in Irvine. False. You know, every time I teach this class, I give this example, and it's never been true yet, sadly. Stuff like, it will rain tomorrow. So this is funny because it was, the truth value is unknown, right, at the time. But then if I say it today and you will examine the statement 2 days from now, you will be able to assign truth value to it. Or chocolate ice cream is the best, right? Like, it's like, who says, right? Well, like I say. So it's a matter of opinion. don't worry too much whether this should be, this is objectively true or false, or whether we will be dealing with these type of statements in this class. So what is definitely not a proposition are, for example, questions. There's no way you can assign truth or false value to a question. Okay, hold on a second. I have to close the window. Sorry about that. There's some noise outside. By the way, somebody is not muted, and their little soundtrack is recorded as I lecture. So just mute yourself if you could. All right. Commands like please come here, have a nice day, they don't have a truth value, right? Another thing, exclamations like "oh my god" or like "damn" or what? Yeah. What's the truth value of that? But this goes really more. So the language conveys all sorts of nuance, emotion, humor. It is self-referential. It is actually a very complex thing. And for example, take poetry or prayer. If you're not convinced that everything has a one-to-one connection to logic, these are the forms of language which immediately make it obvious, okay, that if I say, something is good versus something is not bad, these statements might be logically equivalent, but they are nowhere equivalent in standard speech, right? They have different nuance. They carry some, secret quote unquote meanings, which make a difference, right? So what we do in logic is that we simplify things, and we, just cut out all that elements of language which we, claim are not important for our purposes, right? It's like putting a language into some sort of, torture machine where like everything that comes out has to be either true or false, and everything that cannot be categorized this way is just kicked out. It's something we do because it's useful to study objects like that you do with, in computer science. It might not be useful for everything that you do in life, right? So mapping everything that happens in humans' mind, in rationality, onto logic, it's what we are telling you here. It's a particular vision, if you will, of how you could do this for certain purposes. It's not the only one. Like, for example, this is binary logic. Could you have trinary logic? Could you introduce one more, more logical values? Could you have like an expression for, instead of true and false, could you have a maybe? Could you have most likely? And yes, you could. So, I know a Polish guy who introduced this type of non-binary logics in 19th century. Might have happened, to some other people at some other point in history. And obviously, this is the kind of stuff that happens all the time in our, studies of human things, right? Where like a binary system might be, useful at some points and maybe too limiting in others. It's the status of this mapping between logic and the rest is an endless topic of investigations all over the place, and some of them do carry back into the computer science. So if you think of like, AI and machine learning as basically the quest to understand, to be able to map more and more human activities into some processing, like for example, understanding speech and understanding text. Now suddenly nuances in human expressivity, right? Like they matter. And understanding these actually matter within the computer science context. Okay, but yeah, so that's we take all of this aside, but it's nice to, I think, know that the that there's all sort of implicit assumptions being taken here. So back to binary logic. We will denote propositions with variables. We call them propositional variables. By convention, we'll call them like P, Q, R, S, T, and so forth. Of course, in math, a variable, you're free to call a variable whatever you want. You can call your variable, dear leader, if you want, right? Except that it will be highly non-standard, and everybody who reads an expression where you're calling variable dear leader and dear vice president, right? Could be people will be like, what are you talking about, right? Like, why you chose these particular variables? So we just have conventions that in arithmetics, for example, X is kind of used very often for arguments to a function and Y for a value of a function, right? And not vice versa. So these are only conventions, but yet useful ones. Okay. Because they just allow you to communicate faster with other people and be able to understood. The values are denoted P or F for truth or false. Equivalent, you can use 1 for true and 0 for false. Purists say that you should only do T and F, and once you do 1 or 0, then it's not Boolean logic, but it's some arithmetic rendering of it. It really doesn't matter. People do that all the time. They either use T and F or they use 1 and 0. So both are fine with me. The textbooks uses T and F. Okay, but in real life, you need to know both. All right. So the first logical operation, conjunction. Conjunction is a binary operator, so it takes two arguments, two operands, and is expressed with this funny symbol inverse V, right, with a bird sign. That symbol is read AND. Okay, so we read this expression P and Q. Okay, and now in order to understand what this operation does, you have to be able to assign truth value to the output of this operation, and this expression stands for the output of the function AND applied to operands P and Q. Okay, and here is the definition of how this operation works. So the output of conjunction is true only if both of these operands are true. And in every other case, the output is false. And this agrees with the common usage of the word AND. If I say, I'm a computer science professor and I come from Poland, well, this is true only if, first of all, I'm a computer science professor, and second, I come from Poland. Otherwise, this conjunction is false, right? So here is a truth table for this operation. So truth table is a table that lists. So on the right-hand side of the truth table, the last column corresponds to an expression that we want to, for which we create the truth table. Now we count how many operands are in this expression. Here, there's only two, P and Q. So based on that, we know how many columns we need at the beginning, one for P and one for Q. And what is all this stuff? Well, this actually will list, the point is to create a row for every possibility of P and Q value as a pair, okay? So because P has 2 values and Q has 2 values, the possibilities of pairs is 2 times 2, which is 4, which is how many rows you have. And now you have to have also some systematic method of filling up these rows. So my method is to start with P, the first value, and first of all, give all this, consider this value to be 0 all over, and then consider the value to be truth all over. And how many times? Well, I look at how many times I need the next row. So the next column is Q. It also starts with 0, and then I have to consider Q being 1 as well, right? And so that's my method. The textbook also does it's very similar in that the first value switches values the least, the second switches more, and if there was a third here, then it would flip even more, right? But the textbook starts with true and then has false. It really doesn't matter which way you do, as long as you're systematic about it. Okay, so I mean, you don't want to give a truth table where there is a kind of a random looking permutation of the stuff, because it will be very hard for other people to read it, including yourself. All right, so boom, this is the truth table. All right, so I said conjunction is true even only if both operands are true, and you see it here. I assign the truth value to the conjunction false for all the cases where at least one of P and Q was false, which are these, and the only place where the conjunction was true, excuse me, was where both of the operands were true. Okay. Second operation, disjunction. So disjunction is the birdie going the other direction. So it's a V, and it's read or. So this expression P is read P or Q. And I define the value of this expression to be true whenever at least one of them is true. In other words, the only case where P or Q is false is if both of them are false. So the truth table, and look, these guys have exactly the same structure as people here, right? Because P or Q is another case of an expression that has only 2 variables, P and Q. So this method of filling up is the same. Okay. And but now the function will be defined by how I fill up this column. And it's this, right? Because the only time that that an or expression is false is if both P and Q is false, so it's this row. In all the other rows, right, at least one of them is true. Here Q was true. In this case, P was true. In this case, both were true. But P or Q is true in all these cases. This is a case. This is an operation which we call inclusive OR. Okay, so it's inclusive because it includes the case that both of them are true. So in other words, I say either A or B, but I don't exclude the case that both A and B are true. And like this is a very useful operation in in orthodox computer science applications. Like for example, you want to state a criterion using a disjunction. The criterion is for whether a patient should take a medication. You say the criterion that triggers this is that if the patient has a history of migraines or the patient has diabetes. Now, clearly, if both are triggered, right? Like then you should order more. I mean, right? This rule should be triggered if one of them is satisfied, and if both of them get satisfied, then it's still triggering the rule. It's still triggering the consequent. But sometimes in human speech, you can really be expressing a different proposition. So, for example, I say, I will either drive to work or ride my bike today. If I happen to drive and take part of the way and ride, okay, I guess you can say that I didn't lie, but normally this expresses either or. In other words, one of them is going to be true, but at least implicitly, I suggest here that not both. This is the case of a different logical operation, really, that very often in casual English is used when people say or. They mean an exclusive or. Okay, but in logic, an exclusive or is has a different it's a different operation. It's denoted in this way, like a plus in a circle. It's read XOR for exclusive or, and it's defined differently. It's defined to be true only in two cases, where one of these guys is true, but the other is false, which is these two. Which means in particular that if both of them are true, which would make this or of the two true, sorry, the exclusive or would be false. These are simply two different logical operations. Standard or, the inclusive or, and the exclusive or. Okay, they cannot be confused because one of them is the first one is denoted this way, the second one is denoted this way. So you exactly know which one somebody means when they use this sign versus that sign. Okay. And again, interpreting human speech, it's a different story. Okay, as we said at the beginning, it could be problematic for endless number of reasons. But not in Boolean logic. Once you're on the level of Boolean logic, it's clear what you're saying. Here is another logical operator. It's called a complement. It's denoted with this funny symbol, which is read not. Okay, so when somebody writes this symbol P, this is read not P. Okay, it is a unary operation. So unlike the disjunction or conjunction or exclusive or that we saw on previous slides, this guy acts on a single variable. Okay, and so therefore its truth table is particularly pleasing in its succinctness. It has only one column. It has only input and output columns, and there is only two choices for the input, and it's sweetly does this, right? Notice that this operation, any other way of filling up this column would make this operation trivial. It would be either identity, if you have 0, 1, and who needs that operation, kind of, or it will be a trivial operation which just kills the input, right? So it doesn't matter what the input was, the output is always true or always false. It's kind of who needs that operation either. But this one is very useful. It flips. Okay. So let's talk about compound propositions. So propositions which take a bunch of these operators all at once in some way, in some sense. Let's look at some special cases first. The special case number one is that you take a conjunction, but here intuitively you'd conjunct a bunch of things, not just two. what does such an expression really correspond to? Because so far we learned about how to conjunct two things, not n. Well, I can parse it like this. I can think of this expression as denoting an operation that comes out like this. First, I apply this conjunction to P1 and P2. So in other words, I rewrite it like this by putting P1 and P2 conjunction in a bracket. And then whatever this thing outputs, I take the result and I conjunct it with P3. And so therefore I have these brackets here. Okay. And whatever this came up with, I take it as a result and I conjunct it with P4 and so forth, right? So in other words, I interpret this in this way. And now I can apply what I already know about conjunction as a binary operation, as an operation that takes only two arguments, because now these symbols do always take just two arguments, right? Like, for example, this guy takes two arguments, this and whatever this bracket evaluates to. But I can also go from the other direction, right? Like perhaps I first do conjunction on this side and take the output and I conjunct it with the previous and so forth. The last operation I will do is whatever this whole conjunction gave me, and I conjunct it with P1. So I go in precisely the opposite direction, right? In fact, you can apply pairwise conjunctions in any order. So if you wanted to, you could start with this one and then move whichever direction you want. Take the result and conjunct it with P2, or perhaps take conjunct these two, then these two pairwise, right? And whatever the outputs were, now do this conjunction of this output with this output, etc. You can make any binary tree either lopsided, so depth n in these two cases, or nice and shallow, logarithmic n depth, by doing pairwise here, so half n conjunctions in the last row, in the next one n over 4, in the next one n over 8, and so you have depth log n, which would be particularly good if you were to code it in hardware. Now, why the order of these conjunctions doesn't matter? Why I can be so cavalier in saying that actually you can do any order, either this or that or anything in between? Because if I define C to be this conjunction output, either way of ordering will actually create the same notion of a function that maps n variables into a proposition. So it either assigns truth or false to an expression that involves n variables. And the function is this. The only way this value is 1 is if all of these components are 1. In other words, the only way for this to be true is if all the PIs are true. And you can see that this is true no matter how you evaluate, because no matter how you write this tree of evaluation tree, basically you will do the following. Because it's a conjunction, so the moment any of the two arguments in the conjunction is false, the output of this logical gate is false. And so this will propagate, because the next time, in whatever order you take this false output and conjunct it with whoever on the left or right, it will force the output to be false again, right? Because that's how conjunction works. It's false the minute one of these operands are false. So false will propagate and will basically kill off all the information from the rest and will force the output to be false. So if on the bottom you have 0 anywhere, you have a 0 guaranteed as an output, and the only way you get a 1 is if you start with all 1s. So this way you can convince yourself that the order indeed doesn't matter. So you might just as well skip the brackets, right? And so saying this actually makes sense. Everybody knows how to read this. Just conjunct all of these guys. I don't care what order, because in truth, it doesn't matter what order. A very similar thing for disjunction. So I can write a disjunction of an element, and again, I can evaluate it in, in the left-hand side order, or the right order here, or in anything between, including the binary tree where I'll have depth log n. And again, this is because if you look at what disjunction does, you will notice that it kind of has like an opposite effect of conjunction in the following way, that if you disjunct two operands, the rule is that the output is 1 whenever one of them is 1. So now the flip, this acts like a flip of the conjunction, because now whoever was 0 is forgotten. The 1 dominates. So if the inputs were 0, 1, or 1, 0, or 1, 1, its output is 1. So 1 dominates, which means that the next time this 1 output from this, let's say this gate or that gate or anything in between, if the output is 1, then it dominates whatever comes from the left or from the right. So 1 propagates. So the minute you have at least 1 true among the PIs, the output will be true. And the only way to get the output 0 is for all of these guys to be 0, false, right? So it's exactly a flip of the conjunction behavior. And again, you might just as well skip the brackets, because indeed evaluating truth false of this proposition, compound proposition, does not matter does not depend on the order with which you evaluate these pairwise disjunctions. But that's kind of it. Oh, actually, there is one more, XOR, right? So you can check for yourself that XOR also does not matter. But the reason is, so the ordering of XOR also wouldn't matter. But the reason is different, because its XOR does not have this dominant behavior. Right, that there is any input that dominates all others. 1 in the case of conjunction, and is so 0 in the case of conjunction, and 1 in the case of disjunction. But okay, so a good exercise for you, convince yourself that order in XOR doesn't matter either. All right, let's take this example of a compound proposition and see that, actually the order starts mattering now. So in general, in logic, we have order of precedence. It's fixed. It is like this. Complement, I mean, there's more logical operations, so you will have to expand this list and say what the precedence is involving these other ones. But so far, we have seen complement, conjunction, disjunction, and also XOR, which I don't omit it here. And a complement always acts first. So in this expression, it's not so apparent, but if I put a not at the very beginning, then you can say, well, am I negating just this symbol, or am I negating the output of the whole thing? You're negating just this first symbol, because negations are to be acted first. And then when you have, okay, should I first do this conjunction? So this guy needs to be negated, and that's the first operation. And then, should I first do this disjunction or this conjunction? Well, the conjunction. On the other hand, that's the order of precedence. On the other hand, please do not rely on anybody remembering what the order of precedence is. In practice, people do not remember this. I do not remember this. If you gave me this expression, I would have to check the textbook or wherever on what the order of precedence is, because I would not remember. And I will not test you on remembering this either, because people don't remember this, and you should not rely on it. There are some exceptions to, so I also don't want you to slap parentheses everywhere. For example, complement precedence is what people are supposed to remember. So when you when you write this, you don't have to put brackets here. On the other hand, when you write not and some expression, again, it would be really much better for you and anybody else if you put not and then brackets, no, actually not. So yeah, so because then you override the natural order, right? So you can write not Q here without putting the not Q in parentheses. Also, if you have multiple disjunctions or multiple compound disjunctions or compound conjunctions, don't write parentheses because this everybody knows that the order doesn't matter. So there's basically two things. You don't want this to be too cluttered, because if it's super cluttered, people cannot parse it. But at the same time, it has to be suffice so that people can parse it correctly. Let's look at evaluation of compound propositions. Take these two propositions as examples, and let's plug in some values. P is true, Q is false, R is false. And let's see what this evaluates to. Okay, so first of all, I'm going to replace it by human words because it's easier for me, right? So I'm going to replace this with an or and this with an and. This is just symbols. It's just that these symbols are easy to read. Then negation comes first. So this negation here does not apply to the result of all of this. It immediately acts on P. So I can rewrite it this way. And now I can plug this in, right? So P is true. So this expression is not true. Q is false. So I can stick F here. And this, not R, is not false because R is false. So now I have a fully evaluated, right? Everything, there's no more variables here. Everything is instantiated with a particular Boolean value. So now I can run these operations, right? Which one I go first? Well, this one, because I have brackets here. So without brackets, this would take precedence, but again, I don't like that, right? Like I don't want to rely on that. So false and not false, what does that evaluate to? It evaluates to, well, okay, I guess first I can evaluate the not false. That's a true. Okay, so I go in the order, right? So before I evaluate this conjunction, I first evaluate this thing. So not false becomes true. Now I can evaluate this operation, and false and true, right, is false, right? Because the only way and can give you a true is both of these guys are true. And false or false is a false, right? Because the disjunction is true only if at least one of them is true. And here is the case where both of them are not. Okay, let's do this one. All right, so I just rewrite the operations with human readable way. And I stick in these values, true for P, F for Q, and F for R. Then I evaluate this thing, not F is T. And then I have this compound disjunction. And I know that any order I go, because one of them is T, so the whole evaluates to T. And because I have this negation, the output is false. Now, of course, I didn't have to do it this way, right? Like once you do this a little bit, then you will notice shortcuts. And so you can get to a result sometimes very much faster than this. For example, you might basically not have to evaluate huge parts of these expressions. So once you instantiate these with these values, right? So you see that this is not 2t, or this part Oh, well, then I can just, okay. I do have to still evaluate them. Sorry, I was confused by my own notes. Okay, so what I have to do is, what I could do is forget about this part. So I could just rewrite this as this part. Why? Because if this is false and I have a disjunction, then basically a disjunction of false with something, whatever this thing was, is equivalent to just something, right? You can see that once the first element in the disjunction is false, then the disjunction is equivalent to, is equal to whatever value the second element has. It doesn't speed up the evaluation greatly, it just allows you to rewrite this faster. Okay. So here the evaluation also could be like this. Look, you know that the disjunction is true whenever one of these guys is true. Here already you know that P is true. So you don't need to worry about any of this. You know that the whole thing evaluates to true because of this basic disjunction rule, that it suffices for one of these guys to be true for the whole disjunction to be true. So you can jump from this point to this one just by checking that P is equal to true, right? And so the more you do it, the more you will see these type of patterns, and then you will see like that these patterns actually correspond to certain laws of Boolean logic. Let's do a Boolean table, a truth table for a slightly more complex expression that involves 3 elements. So it's an expression involving P, Q, and R. You have, let's write the truth table for this because the expression has 3 variables, so we need 3 columns for these possible values of these 3 variables, right? And now this guy has 2 possibilities, this one 2, this one 2. So there is 8, 2 times 2 times 2 of all of them. I need 8 rows. And I will fill them up with my convention, which is start with zeros, then go to ones, and let this first guy has like the varies least. So first everything and then everything of the other kind. Make this guy flip with, you know, 1 less frequency, and make this guy flip with the most frequency. Okay, and this is like a methodological attitude to this. Okay, and now what kind of expressions I have here? So I know that to evaluate this disjunction, I need to have not P and the result of whatever this is. So I make a column for not P to just make this evaluation easier. Now, because this is Q and not R, so I need to know what this thing is in order to evaluate this disjunction. So I make a column for this expression, for values of this expression. And this expression has Q, well, I have a column for Q, and not R. Well, so far I don't have a column for not R, so I create one. And basically the number of columns is the number of operands here. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and also in the order of evaluation. These guys, you will evaluate them first in order to evaluate this, right? So this is in order of evaluation, although I guess you can flip these 2, right? The rest wouldn't matter. Okay, so in order to evaluate, fill up this column, what do I need to know? Well, the only thing I care of is this column, right? Because not P doesn't care about Q and R. And what does a not do? It flips. So this column is just a flip of this one, right? Easy does it. You take the values here and you flip them. Next one, not R. I only need to look at the R column. Again, these 2 columns don't participate. And what do I do? Well, it's a not, so it's a flip. So whatever value I have, I negate it, I flip it. From 1, I go to 0, from 0, I go to 1, etc. I don't really have to look at this stuff much. I know that this is 0, 1, 0, 1, 0, 1, 0, 1. So the minute I know this, I just copy it. Okay. Now, what about this? Okay, so the next in order of evaluation is this conjunction of Q and node R. And I know the conjunction rules. The rules is the value here is 0 whenever any of this or that is a 0. And the only way I'm going to find a 1 here is if the row, if in that row, both this column and this column was a 1. Okay, so the reason I put zeros here is because this Q was 0 in these two cases. And in fact, by rules of conjunction, the minute I see a 0 here, I don't even have to look at what node R is. I already know that this is forced to be 0. This guy I have to look because this guy is 1, so therefore I have to check what is the value of node R. It's 1, so I write 1 here, and in this case it's 0. 0 dominates in conjunction. Here, because 0 dominates, so the moment I see zeros, I again copy them. And here I do above, right? In fact, this thing is a copy of that. Why? Because the only difference between this half and this half is the value of P. It was 0 here, the value of 1. Otherwise, everything in this upper half and lower half is a copy. And because this expression didn't involve P, I really might stop evaluation here and just copy this part as the upper part. Okay, but all right. Now I take node P and I take this column and I disjunct them. Because here I had a 1, I don't really have to check what this is. 1 dominates when I evaluate disjunction. So the minute I see all 1s here, I just copy them. Here it's all 0. So at this point, the disjunction is an identity on the second variable. So you might notice that this thing is a copy of this thing. That's exactly why, because the second element of this junction is a 0, or rather the first. And so at that point, when constrained to a false for that, I just copied the second, whatever this value of this thing was, right? So here so that's how I evaluate these compound expressions. Let me maybe end with the following. Let me see if yes, logical equivalence. So two compound propositions can be logically equivalent if they have the same truth value for every combination of input values. Right? If one expression is a function of, say, 3 variables, ABC or PQR, and the other is some Boolean expression, compound expression, involving the same variables, PQR, then, well, these are some, however complicated expressions involving the same. So there will have a truth table, which will have 8 rows, because it's PQR, so it's a triple of Boolean values, 2 for each, so 2 times 2 times 2, 8. So the expression number 1 corresponds to some column in the truth table, some vector of 8 true-false values. The other expression also corresponds to some vector of true-false values of size 8. If these two vectors are identical, the two expressions are equivalent. Okay, they have the same value for every PQR choice. Here is an example of two expressions involving just 2 variables. So the truth table has only 4 rows, and not these 2 expressions, not conjunction of P and Q, and a disjunction of not P and not Q have the same vectors, have the same truth columns in the truth table. Why? Well, do a conjunction on P and Q. It's 0 everywhere here, And the only place it's 1, it's here. But because you have a negation, so you flip that. So it becomes the negation of a conjunction becomes 1 everywhere here and 0 only in the 1, 1 row. Now let's look at this thing. It's a disjunction of negations. You know that the disjunction is true whenever any of these operands is true. But because operand here was flipped, so this becomes true whenever one of these was false, right? Because if the minute P was false, so not P became true. And if not P is true, then you don't have to worry about this guy. This disjunction becomes true. Conversely, for not Q, the moment not Q is true, this disjunction has to be true. Not Q is true whenever Q is false. So if Q is false in these two cases, this disjunction has to be true. And the only case left is this one, which is false indeed, because not true is false and not true is false. So it's false or false, false. There is a deep reason for this, and it's called De Morgan's law. And that's where we will start the next lecture. And I keep recording, but I will open up for questions. So go ahead. If you have any questions, speak up.
Hey, I don't know if you saw what I put in the text, but
Not yet.
This feels like it's redundant with 6B, basically, or maybe the
Yes,
sort of.
It is. 6B does the same thing. Yes, we intersect on chapter 1. 6B does chapter 1, we do chapter 1. It's only the first week of the class, but it is redundant indeed. Yeah. So for everybody who took 6B, it's a review. So yeah, sorry about this, but it's like this is like an endless debate that you see at ICS. Should we keep on doing it? It's like this is a result of like basically that we want people to be able to go as fast as possible because there is so much stuff that we want to teach, and so therefore it is designed so that you can take 2 classes in whatever order. Yeah, it's I don't know whether this is still true, but for a long time it was true, and I suspect that this is still true, that CS degree is kind of packed with stuff. So it is not, we want people to be able to go through it easier, and this is something we came up with. Not me personally, but I do understand that that's the reason. So there's too many questions in the chat. So if somebody has like a very big question, please speak up. What will be happening in discussion? Somebody asks. So some of the discussion leaders have posted some here is the stuff I want to do. I noticed one of them like didn't set the what's it called, permissions correctly. At least for me, when I go, it blocks me. So if you want to see before, some of them are saying, I'm telling the discussion leaders to discuss this material, in particular influence, like by what kind of stuff is asked on homeworks, and they're picking exercises to go over where they think is most educational. In this way, you perhaps will get different people covering different things, which will only, I think, be helpful, because you can watch 2 discussions if you want. So speak up, because reading the chat doesn't give me a clear clear sense of what's at issue.
Someone asked if you have a preference whether we use true or false, and then 0 and 1. Okay, thank you.
You should learn both, because that you will see people use both. Well, I mean, either one. I mean, it's crazy to use both in the same expression, right? But you should be aware that both are possible and what they mean. So the book does T and F, and I do in lectures 0 and 1. This should attune you to the fact that both that these are equivalent approaches, and that you should be familiar with both. Discussions optional. Look, everything is optional, if you want in this class, right? I mean, but I think that they're very helpful. Yeah, sorry, tests are not optional. Yeah, so upcoming homework deadline, yes. And also the readings, yes. Okay, I think that this is going to not look very well on people who watch this at home. So I'm going to stop recording now. And if there is no more questions, then I will sign off. All right, so I take it to be a no. So see you all later. Hope that was fun. Got you in the end. Thank you. And by the way, if anyone knows how to preserve a chat, because I feel that although I cannot read all of this, that maybe you are having some discussions among yourselves. And for example, that you want to, save something. Let me know if there is some fast technical solution for this, because basically the moment I close, then this kills the chat and it makes it go into a dark hole. When do I turn in the homework? Where? Grade Scope, and I haven't set it up. So I will set up the site. I will post on Piazza when the Grade Scope site is running. So somebody says that I could record the stuff. Please, could you put it on a Piazza? Because I think that there's also like some complicated thing that is like privacy. Like, so one is that people, I don't want to lose some stuff, and maybe you don't want to lose some stuff. On the other hand, some people maybe want to lose that stuff, right? Because they do some sort of quick message to one another, even on a private chat. So post it on Piazza, and would you? And then maybe we can have a discussion, maybe we can have a vote for whether majority of people want this chat to be saved or not. Okay, I understand. Thank you, Isabel, that like save chat is only text file with timestamps. Save chat. Oh, I see. Okay, well, I will. Easy does it. Okay, I guess I just saved the chat. And I have like a crazy list here now with timestamps and people saying hello, happy Monday. All right. Well, okay, you know what? This is good for me. So I'm going to like save a chat for myself. And if I see some question that somebody asked and I feel like I should basically post it on Piazza, the answer, then I would do that. Okay, thank you. Thank you for pointing it out. I have now like this chat in front of me now with all the questions and answers. Okay, so nice chatting with all of you, but I will switch off. I have to go to some next thing. All right. So I'll see you office hours Tuesday, Thursday, 9 a.m. and lecture Monday, Wednesday, Friday. Bye, everyone.